Great, so this is question 2.3. It's called delete middle node, and it is exactly what it sounds like. We want to implement an algorithm that deletes a node that's in the middle, and they just specify that it doesn't have to be necessarily in the exact middle of a singly linked list, and we're only given access to that node. So here I just wrote out a linked list where I use the node class that's provided in the book, where we just have a constructor that passes in the data or the value that's stored in that node along with a pointer to the next node in the list. So we just create a list that is just 1, 2, 3, 4, 5. And then we just call our method that we have to create, called delete middle node. And afterwards I just wrote the logic that iterates through our list to print it when we're done. So to do this, the first thing that we're just going to check is if our node is equal to null, or if our node is equal, or our node.next is equal to null. I can't type right now. Great, so because if our node equals null, then obviously it's not a middle node. It's the end of the list, or it's just null. And if our node.next is equal to null, that just means that it's the last node in our list, so it's definitely not the middle node. So here I chose Boolean. Sometimes you can just return null here, but we'll just return false in this case because, well, we certainly didn't delete anything, and we're going to return true at the end once we've deleted our node successfully. So the key word kind of for this is we're only given access to the middle node. And so that means you can't really iterate through the list. We're just given this middle node and we have to delete it. And so the way we do that, and I'm just going to write out the logic first, is we set our node's value equal to our node.next.value. So the node that comes after this middle node, we're grabbing its value and we're setting it to our current node. And then we're going to set the pointer to the next node equal to our neighboring node's next node. So that's the algorithm right there. We can run it, but I'm going to explain in a sec why this works. So, and we just have, and that's just because I say value, but the class that I implemented as actually using data. Great, so it just printed out 1, 2, 4, 5. So we just deleted successfully node 3, which is a middle node. And so to kind of describe what we've done there is we were past this node, number 3, and what we did was to delete this node from the list. So we want to delete this node, is we set 3, and I'm just going to erase this here. We set 3 equal to our neighboring node. So our number 3 was pointing to number 4. So we are setting the value equal to the next node. So 3, we then set it equal to 4, right? And then what we did was we set the next node from our current node equal to our next node's next node. So our next node was this number 4, and we want to set it equal to its next node, which is 5. So what we do is then I'm just going to grab my eraser, just kind of erase this here, is then we actually set this next node, we point it to the number 5 here. And so then we're essentially erasing this relationship here. So now when we iterate through our list, starting from the first node, it'll go 1, then 2, then 4, and then 5. And so there's no way to get to this node because, well, there's no relationship here at all. So it's not a doubly linked list, so there's no way to traverse back from 5 to 4. So we're simply iterating through this list, and we've successfully deleted the third node. And so that's the algorithm, and the performance for it is just constant time space and constant time complexity. We didn't use a hash set or any extra data structure to do this, and it's constant time because we're simply performing constant operations. So great, I hope this helped, and good luck with the rest of your algorithms. Have a great day.